All right. All right, a lot of people. Good morning, everyone. People are trying to like find themselves in the middle of this beautiful sofas. I have to say that I really like this area. It's really cool. It looks like a cinema, really. Wasn't expecting this at all. All right. So my name is Italo. I work at N26. I'm an engineering manager over there. And today I will be talking about designing for failure. So just one question for whoever wants to answer, like who knows what is designing for failure? What is designing for failure for you? Does anybody have any comments on that? Yeah, that's a good way of putting it. So what I want to bring today for you is a few concepts of how we can design system for failures. So this is not specific to Go. This can be applied to any kind of language. But I really like Go. I really love Go. I've been developing Go since 2013, more or less. And then that's why basically I've brought this topic here. So basically, we want to design systems for the unexpected, right? Things fail all the time. And we never know when they're going to fail. But when they do, it's basically when you're losing money on your company. It's basically when your users are not really liking the experience on your apps or systems or anything that you actually do. So how can we design better systems, better software, so we can have a better reliability? Is there any site reliability engineer here today? Any SRE? There we go. All right. All right. So before we start this, I want to go over a little bit of history. I'm very passionate about airplanes and aviation of all kinds. So I want you all to think about an airplane, especially like the 777, and I'm going to tell you why. So a Boeing 777 was developed in 1993, right? And at that time, there was a system designed internally in the airplane, which is called ELMS. So electric load management system. Is there anybody from aviation here? Like the likes of it? There we go. Nice. Yes, so this system was also designed in 1993, and it's a very fantastic system. It's actually working till these days. It's a very reliable system. And think about when you get into a plane, and you sit on your chair over there, and you fly, right? Now, there was an incident that happened a while ago where one of the engines of the airplane actually caught fire. That's probably not something that I would like to experience in an airplane, but sometimes it happens. And when it got fire, a few people, of course, saw it, and all the lights inside the plane actually turned off. And you know the air conditioning that comes out of the plane, also on the side, are actually turned off. So the masks fell down, and people were, of course, getting scared, but why did this happen? And there was a failure in the engine. Nobody was expecting that. But this system, in 1993, was designed so we can actually do concepts that we can apply to software today, which is load shedding, or fallbacks, or, well, basically graceful degradation of your system, so you can actually survive with a very basic essentials, and that's what you really want. You want to keep the plane flying so nobody actually gets hurt, and those systems in that day was actually designed for this already. And I like to take this example because we do that, like we design software, and I don't know if there is maybe a few of you that actually design mission critical software, like for hospitals or airplanes even. You're putting people's life in risk, and you have to put resilience as your first priority, right? And I like to take this quote. Does anybody of you also ever read the Airbnb articles on Medium where they speak about how they design their software, like their system? There is this quote, like, resilience is a requirement and not a feature. And I really like this because if you think about mission critical software, that's like your first class citizen. But when you are talking about day-to-day software, like you're let's say working in retail or fashion, sometimes you don't really think about resilience. Sometimes we just let it go. And when the things actually fail, when the systems start to fail, then we start thinking about resiliency. That's what I would like to change. That's the cultural change that I would like to bring up, and maybe we can pay a little bit more attention to this. I wasn't paying attention to this like for a long, long time until I actually realized how important these things are. All right, so we can start with one thing called dependency isolation and graceful degradation. And essentially, dependency isolation, if you think about a system, if you think about a microservice architecture especially, or any distributed systems, you know that the first thing you have to start with is always mapping out your dependencies. So you build a system, and what you really want to do is actually, okay, I depend on service A, I depend on service B, I depend on Kafka or Rabbit, your databases, anything that actually is an external to your software. And out of that, this kind of dependencies, you need to start putting a few things into place so your software can fail gracefully. And identifying those dependencies is critical, especially when you're like before creating your system. You want to know, okay, what is critical for my system to work? So you think about the example that I mentioned before. That system was designed thinking about what is essential for an airplane to keep flying. And you can apply the same concept when you're designing your systems. What is essential for your service so it keeps running, so you still can provide content to your customers or to your users or to other services. So we always start with health checks. And who here develops in a distributed system architecture? All right, quite a lot of people. Who here actually do proper health checks, like checking your dependencies? All right, not so much, not so many people. And that's normal. Like up to these days, I wasn't really paying attention to this at all. I used to work at HelloFresh as well a while ago. Over there, we were doing Go quite heavily, and we started developing a few things to start checking. Okay, how our dependencies can be mapped out. How can we make sure that our container orchestration system can actually look at these health checks and can make sure that it only removes your instances out of the load balancing algorithm when your service really cannot serve requests anymore. So for that, can you see this? Yeah, sort of. Okay, so this is just one of the libraries, right? There are many libraries in the. If you go to AwesomeGo, you can quickly check that. This library is from InVision, so InVision Go Health. It's an interesting library because it is standardized how you're gonna get your dependencies, how you're gonna communicate your dependencies to, like to container orchestration or to whoever is checking your health checks. And what essentially it does here, like you create an instance of health, and then you start creating checkers, right? Like it comes with a few checkers, like SQL checkers or RabbitMQ or AMQ actually. And you just need to add the checkers that you have, and then later on you're gonna, this is really interesting, like, is this a fatal dependency? So that's why it's very important so you map out your dependencies. Because let's say that you have a system where you are actually sending messages, right? Like you save things for a database. Let's think about an orders example. There's always a case. And you get a request for orders, and then you save the order, but your message broker is not there. Should you fail? Like, should your software stop if your message broker is not there? It really depends, right? If your system can handle eventual consistency, great, then you don't need to fail. If your system really depends on, like messages going through, either you might want to redesign it, or your system this is a fatal dependency and cannot fail. So once you map this out, what really happens, if everything is okay, if nothing is failing, you get a standardized, well, this is like a JSON representation. You have many different ways of representing this, but the important thing is the 200 on the HTTP check. Normally, if you tell like Kubernetes or Nomad, you can tell them to check this endpoint, which normally is like /health or any other endpoint you like. And it gives you this, right? It gives you like saying, okay, everything is fine, your dependencies are working, nothing to worry about. If things are not so good, but your app can still work, normally what is going to happen is something like this, where it pops you an error here saying, okay, something is happening, and you still get a 200, because your app still can serve requests. It's just you're probably going to experience the eventual consistency. Things are not really working the way you expected. And this, I'm going to talk in the end, but this normally also triggers your monitoring system and alert systems and so on and so forth. Now, if things are really bad, what you expect to happen is that you get a 500, and then you actually state, okay, why is my software failing? Now, why is this 500 important? It's basically going to tell your container orchestration system, if you use containers, or whatever other orchestration system, that your instance is not healthy, right? That it needs to be removed from the load balancing algorithms, that it needs to be either brought down and then spin up a new one, or that you actually have to do an action, like an interaction, like a human interaction. So health checks are quite important. If you don't do it today, maybe you want to start thinking about having these standardized ways of checking for your application's health. It's very, very important. The second thing is because this will bring self-healing into place. And self-healing is a critical thing when you go to a distributed architecture, right? Like, you're dealing with like tons and tons and tons of services. Let's say you have a microservice architecture with 500 or 1,000 microservices. You really don't want to touch your containers. You really don't want to go to your pods and actually say, okay, please spin up a new pod, make sure it works. So you want a container orchestration doing that for you. Or if you work in AWS, you want the EC2 instance kind of self-healing as well. Now, as I said, containers orchestration normally do this for you. Like if you use Kubernetes, you can configure it. So you say how many instances you actually want of your application running, so on and so forth. All right, load shedding. Who does load shedding today in your apps? Who knows what load shedding is? All right, so you do it. Beautiful. So, all right, load shedding is something, again, back to the example before, back to the ELMS, so electrical load management system. Load shedding, remember the engine actually breaking example that actually happened. So what happened internally, why did the lights turn off, and why did the air conditioning stop, and why did the masks fell down? That's all because of load shedding. So what the ELMS system was trying to do was, all right, most of my batteries are broken. So if you know, like the engine, like in the turbine, basically what happens is like the wind goes through, and normally that wind makes some power into the thing that actually rotates, and that goes into a battery in the airplane. Normally a Boeing 777 has like about 7 batteries, just in case one fails. That's the fallback principle, right? If one battery fails, tries another one, and another one, and another one. It's good that we have 7, because you know, it's sort of an airplane. So load shedding, basically, because one of the engines was actually broken, the system automatically detected that and start directing every single like required capacity that it had to keep the main controllers, or the ATC, or ATC is Air Traffic Control Command, making sure the plane still works with the very basics. So he had to turn off like energy or power from the air conditioning and from the lights of the airplane, and make because the cabin is pressurized, so the things actually fell down. Right, circuit breakers. Anybody use circuit breakers? Yes, good. All right, so circuit breakers is nothing new, right? Like if you think about your house, you normally have a circuit breaker where you can turn off each room in your flat or anything like that. The same thing applies to software. Circuit breaking is something that is critical for, let's say, for your external dependencies. Again, mapping your dependencies out is important, because once you identify that, every external call, you can actually just wrap it around a circuit breaker. And the reason why we do this is because what you really want to achieve is to make sure once your call, like once your external dependency starts failing, what you really want to do is, okay, my requests are failing. After a specific threshold, I want to make sure the circuit is open, so no requests go to that specific service. So this is, again, an example, like Hystrix, just one note here. Hystrix has been deprecated. I've put it here as an example, but Hystrix is a Java-based circuit breaker system where you can monitor it. It's more like a standard than just a thing on the language. But Hystrix has been deprecated, but we still have the library for Go. It works really well. But there are many, many libraries that you can check. I will leave a few links at the end. But you can check basically this. So what we're doing here is that we create a Hystrix client, right? So let's say an HTTP client. Let's say you have to call a payment system. And that's a mission critical kind of dependency. You have to have it. And then Hystrix, you create a client, you put an HTTP timeout. Very important that you set your timeouts when you go to external HTTP calls. Normally you give a command name, and that's from the Hystrix standard. And then afterwards, you say, okay, this is my error % threshold, so I can fail 20% of all the requests. These numbers, you don't just randomly put there. You normally guess as time goes, right? Like, I'm going to show you at the end about SLIs, SLOs, and SLIs, and how you can bring these numbers to a more precise number that makes sense. Right, and then we do this, and then we set this leaping window, which says, all right, I'm going to, like, after 20% of errors, I'm going to wait 10 seconds before I can actually retry. And then you just say the request volume threshold, which applies the same principle. And then a fallback function, which is going to be when a circuit trips, that thing gets called. So you can do whatever, right? I just put an example there. But you can log, you can alert your systems, you can try to put it on a queue and then retry it. You can do a lot of things. Right. So this is more or less like, oh, this is very bright. All right. This is how a dashboard kind of looks like on Hystrix, right? This is going to tell you all your circuits, if they're open or not, how reliable they are. And this is sort of like your toolbox for monitoring as well. So you can integrate this with, if you use, maybe you use Grafana, you can put this on Grafana. You can actually put this on Graphite and query from there. You can put it on Prometheus and expose it. So you can do really, really interesting things with this. But circuit breakers by themselves are not really useful. Like, a circuit breaker is going to just open and remain open if you don't do anything. So normally you have to apply a retry logic. You have to say to your system, okay, please retry this. Like, my calls are failing, and I want you to retry after a few times. So this is more or less how you can configure a retry mechanism. I like this library quite a lot. It's called Heimdall. And it's just a client, right? It's an abstraction on top of a client, which implements the Hystrix pattern. It also has some retry. Oh, this was not supposed to happen. It also applies some retries. And then you can have something called exponential backoff. So the backoff is basically how, which kind of strategy you want your retry to take. So an exponential backoff is really interesting because exponentially grows the time that it waits for your system to be recovered. So if you have a dependency on service B, let's say, service B is failing, normally what happens when you don't have any kind of load shedding mechanism, think about service A calls service B calls service C. Service C starts failing, and then service B starts failing, and then service A starts failing. That's called cascading failure. Does this sound familiar to anyone? Anyone have been through this kind of thing? Yeah, it happens. Cascading failures are probably the more complicated things for you to debug in a distributed system, because probably a lot of people are running around trying to figure it out, okay, what the hell is happening? How can I fix this? What is failing? and you think service A is actually failing when actually service C is failing. And of course, you don't have tracing in place, so you don't know what is happening. So you are really, really in the dark. So retries, they basically try to, once your service C comes back, it tries to make sure you can just keep working as normal. Right. Another way of having some sort of like limitation when your service is failing is rate limiters. Many times I used to think, at least, that rate limiters were more like a thing that you put on your gateways. Like you put on your API gateway, you protect external requests, you try to avoid the DDoS. But you can actually apply this internally, right, in service-to-service communication. Now, rate limiters are quite simple to use. They're quite easy. There's a bunch of libraries over there. You can do your own. You don't need to use libraries at all. But there are a few caveats. You have rate limiters that are, well, local rate limits using in-memory, but there is distributed rate limiters, which is a little bit more complicated. You need like a Redis instance somewhere, or a Memcache instance, whatever you can actually store something, so you identify if between your instances you can still request, you can still reach that server. This is another library. I will post all the links at the end, which is easy. So you just say, okay, you have 100 requests per hour, and I'm using just a in-memory store, and actually you can apply this. There's some middlewares that you can put into your HTTP client, and this works really well because it helps you kind of like have this this protection of your service if you don't overload your resources, which is really good. Now, Bulkhead. Who heard about Bulkheads? Right, not many people. So Bulkhead, a little bit more history. Anybody watch a Titanic? Ever? No? God. All right. Titanic, very big ship. Very interesting. All right, Titanic was like in if I'm not forgetting this, 1906 or 1912. I don't remember really well. But basically, the Titanic, well, sank. And there was a huge iceberg, and they saw that too late, and then it went down. Essentially, bulkheads were designed. This is really bad resolution. All right, bulkheads were designed in the Titanic, basically skeleton. So this concept was really nice, and this explains why Titanic was going to sink. So if you see these numbers, or try to see these numbers, like we have 1, 2, 3, 4, 5, those are basically the bulkheads of the system of Titanic, right? These are the compartments. The iceberg actually hit this part over here, so 1 to 4, and there was a failure in the system again. So basically, the water starts getting into here and then going up. A bulkhead is supposed to contain the water, right? Like new ships today, if it hits an iceberg, the same way the Titanic has hit it, the water will stop here. But in that time, there was a design failure, and you can search that on Wikipedia and stuff. The water went up into the compartments and to the second one, and then start filling up into the third one and fourth. When you reach the fifth, the ship could not support the weight and start sinking. So bulkheads were created here, and that was the huge, from the architect that actually designed it, was like the main advantage of Titanic. It was the unsinkable ship. Problem is there was a huge flaw in the design. So it went up and down, up and down. So the reason why I tell you this is because bulkheads in software has the same principle. You want to make sure that when you're calling an external service, your external dependency, you're isolating your pools. So if you come from Java, you have the thread pools normally, and you can actually divide one thread pool per dependency, or you can shard the load across different databases and say, okay, I have one thread pool specific for this. Why do you do that? Because if that specific instance is overloaded, your same client, the same client that you're using to talk to that specific instance, is not going to break because of that, because only one thread pool will be kind of like acting weird or blocked. If you think about Go, we have, so Heimdall, the same library that uses histories underneath, also applies Bulkhead kind of principles. So if you have something like an external dependency, we have Go routines, which is going to be blocked, but no, not all Go routines. So your external calls are not going to fail completely, only a few of them. And then we have Outlier server host detection. This is an interesting one as well. But normally, we don't really do that by ourselves, because it's very hard to do it. But just to give you an example, think about you have a system again, like 3 or 4 dependencies, right? Like you depend on service A, and service A has 10 instances. Now, if one of the instances are down, like you probably are doing client-side load balancing, so you're trying to balance that across all the service A instances. And one of the instances is misbehaving, right? And what your algorithm should do is take that instance out, is make sure it doesn't send a request to that. Why? Because otherwise, 1 out of 5 requests are going to fail. And then your availability becomes all messed up. So Outlier server host detection is something that, well, basically I've learned really recently on the Airbnb blogs that I mentioned you, and try to apply in Go as well. So at the end, I will leave a link to a full working example where you can check how this is implemented. It's not difficult, but I wouldn't recommend implementing by yourself. There are tools that you can use. Outbox pattern. Anybody uses outbox pattern? No. Okay. So outbox pattern is, let's think that you, for example, have Kafka, and you're sending messages to Kafka. Let's say Kafka is not there anymore, and your service starts failing, and Kafka is required to be there. So the outbox pattern basically says to you that all the messages go to your data store instead of Kafka right away. So you're going to always save your messages into the database or data store of your choice. Then you have a listener or someone in another thread which is actually going to get that, make sure it tries to send to Kafka, and if Kafka is not there, puts back into your database, and it doesn't dispatch the message. So it tries and waits Kafka to be available. Now, this is more or less how it looks like. This is a library that I created, so there's not many things like that in Go so far. A lot of people do this, but they implement by themselves, so there's no like open source tool that I know of out there. So essentially, I'm just using an example here with Rabbit and Postgres. So we create a new instance of Postgres, and basically like the connection, we pass the connection to that. That creates a data store. A data store is simply an interface where you can just pass whatever implements that. And second one, you say, okay, this is my event stream, this is my event broker basically, and there I'm using just Rabbit. And the check interval says, okay, how often should I check for new messages in the database? And the cleanup is that, okay, messages that were already sent, I can just remove it. So with that, you have a single interface for sending messages, essentially. So you can send whatever byte, whatever slice of byte, and with that, it automatically put that in Postgres, and then you have this start over there, which is just starts like 2 Go routines inside, and then it starts checking for new messages and tries to send you whatever event stream you pass it on. This makes sure that if your event stream is down, all right, no problem. Your message is still going to get delivered at some point when your event stream is back. Now, if your database is down, then that's another problem, because then that's a hard dependency that you have. If your database is down, your service completely stops. Yeah, so this is more or less how the outbox pattern works. There is an extensive documentation about this for .NET, for whoever comes from C#. I used to do a lot of things in C#, and Outbox was one of the things that I liked a lot over there. Right, but all of these things that we've been through right now, they're very, think about trying to develop a microservice from scratch. Now, try to implement all of that at once. try to convince your PO of doing that. It might get complicated. So you, of course, don't want to implement circuit breakers, outlier service detection. You don't want to do that. You want a service mesh doing that for you. So anybody heard of Istio? Great. That's a service mesh. Envoy, blah, good. All right. So those service meshes, they normally come with all of these features that I just mentioned. All you have to make sure is you enable them. So you actually put them to work. You normally have circuit breakers, you have retry logics, you have outlier detection, you have, well, the outbox pattern is really specific, so it's not going to be there. But it protects your database calls, it protects your RabbitMQ or Kafka calls, or whatever other IronQ or whatever. It protects any kind of external service you might have. So you want to use something like Service Mesh. It really helps. And there is a lot of other things that comes to observability. And nothing that I showed here is useful without observability. So what you normally want is a system that you can rely on. Who works with SLOs and SLIs? There is an SRE here, so I assume you do. All right, good. So SLOs, so service level objectives, and SLIs, service level indicators, are the key thing for you to identify how healthy your system is. Without these two, it's going to be very hard for you. You're just guessing what is happening. You might have your monitoring tool set up. You might have like Grafana's dashboards already set up. But if you don't define these two, and this is a cultural thing, it's not a just numbers, right? Like it's a culture that you have to implement in your company or in the project that you're working with. And these two things are going to give you a bigger visibility of how healthy your system is. It's going to make sure that you know what you look for when you are defining those metrics, those thresholds. Now, monitoring is critical for that. You can create the dashboards. If you use Grafana, you can version the dashboards and like deploy different Grafana clusters and make sure you have all of this visibility. And all of these things that are in the service mesh can automatically trigger alerts on Grafana. So that's easy as well. All right. Then we have this. Anybody heard of OpenCensus? Yes. Thank you, Basim. All right. So OpenCensus is something really cool. It was developed by Google, essentially, like Google developers. And what it does, it tries to standardize the way metrics and tracing are actually reported from your application. So this is cross-language as well. So it goes for Java, for C#, for whatever, Python, and of course Go. So it's very simple. So your code doesn't really change.